Welcome everyone to this session of Shadow the Scientist. My name is Jamaica Marshall and I am the Shadow the Scientist Programs Manager. Now, Shadow the Scientist is an initiative brought to you by a team at the University of California, Santa Cruz. As you know, you're in for a wonderful session with your science host, Dr. Viraja Katu, and remote observers, Jessica Nagasako and Lisa Wells. So without further ado, there's Lisa coming on screen now. So we have all three of our main science hosts, our main science host, Dr. Viraja Katu, and then our remote observers, Jessica Nagasako and Lisa Wells. They're all three ready to get started. So let me head over to Dr. Katu to get us going. Good morning, Viraja.
Good morning, Jamaica, and aloha, everyone. I am Virasha Khatu. I'm a Canadian resident astronomer at the Canada-France-Hawai telescope here in Waimea in Hawaii. And tonight with us, we have our two remote observers. So first is Jessica Nagasako. She has been observing all night, so it's end of her working night for her. And then we have Lisa. She is also our remote observer who's going to help us out during the event. Okay, all right. So I think we'll get started with where we are right now in the night. I know I'll introduce CFHT formally, but because we are actually taking standards right now, so these are calibration images. I would like to show those to you. So just to turn over to Jessica, if you have a minute or so to explain what's happening right now in the control room.
Right, so right now it's 5 a.m. Hawaii Standard Time. I'm taking the standards. We have 13 minutes left of science, roughly, and I'm about to end things scientifically for the night so I can move on to take flats. I just finished doing the 5 a.m. weather update. I do updates every hour. I'm writing comments for all of the observations I do. I'm a bit all over the place right now, but I'm here for y'all. And that's what's happening right now.
Okay, so we are currently taking standards, and these are basically a set of calibration images where we are just observing the sky where we do not have patches of clouds. And we want to do that because we want some nicely calibrated stars in order to flux calibrate our actual images that we do take for the science. So this is how we actually see the image once it's taken with the camera. Right now we have MegaCam, which is our wide optical camera on sky. So this is basically a 40 CCD mosaic image. And the statistics that all the data that you see on the left-hand side, on the top left-hand side panel, that is from the green rectangle, which is marked on the image there. So this is just to understand what are the scene conditions, what's the image, which part of the sky it's looking at, and stuff like that. So I'll probably turn over to Lisa and Jessica to tell a couple of things about what is it exactly that they're looking at when they take these images, just to make sure everything is in place and everything's going right. So maybe Lisa?
Yeah, when we get an image off of the telescope, normally we are looking at the image quality, the measured arc seconds of how big the stars are, so that we know we're within the parameters of the program. For standard stars, it's actually quite lax, so we can go up to 1.5 arc seconds for those. But right now it looks like we have pretty good image quality, and so the stars look pretty small and quite round. So when we get that kind of seeing, we do our highest priority targets. And at the end of the night, we're usually doing the standards because they're very short exposures, 2.5 minutes or less. And we can fit those in at the end of the night and do as many of the filters as we took during the night to calibrate all of those images. So.
Yeah, so it overall, I think it turned out to be a pretty good night, Jessica, right?
All pretty good. Around 12 a.m. I don't know if there's any way to show
Blew up a
that.
little
The scene just blew up.
Okay, I can
The
actually
image
share.
quality became pretty bad, but then it's one of those nights where the image quality would go up and then it'll drop out of nowhere, and you just gotta find those nice moments where you can get as many like good high priority targets and as much as I can. And I think I was able to do that. But of course, as soon as the night ends, the image quality gets really great. It's like, where was this earlier? But
So
it's okay.
that's the kind of sky what it is right now. This is from if I go
Wow.
back. So this is a set of the set of monitor screens that we have over here in the control room. So just to situate you a little bit of where we are, I can actually show you. Okay, so if you look at the big island, we are on the big island, but we are not on the top of the mountain. So this is just an elevation difference. We're not on the mountain. That is where the observatory is. We are actually over here in Waimea, where our headquarters is. We are in the control room. It's 3,000 feet above sea level, so it's not exactly sea level, but we are still pretty down. The mountain is 14,000 feet, so it's pretty up. So that is where we are in the control room. And what we have over here are in front of us are a set of monitor screens which allow us to monitor the conditions up at the summit. So this is from one of the all sky cams. And that is when we keep monitoring what's happening, how are the clouds changing, or if there is any fog coming in. And then there are different directions in which we can look at with all of the different sky cameras, which are at different observatories on the summit. So Jessica, do you want to talk a little bit about how you have been monitoring conditions throughout the night? What is it that you did when you got here beginning of the night?
Yeah,
Just to get you started?
Yes. So at the very beginning of the night, we go through our checklist. We have one that we do every single night where we go through the entire building to do a security check. I go through all the different machines, like the hydraulics, to make sure there's no oil leaking, to make sure our telescope is parked, things are out of the way that where the telescope is going to slew. And then based on what instrument we're looking at, excuse me, like tonight is MegaCam. So specifically, I have to like open up a specific guider for that. And also overall, like making sure the weather is looking good. For the past few nights that we've been having fog, we've been having clouds, but this night we miraculously didn't have clouds, but I still had to keep watch and these cloud cameras to make sure that fog isn't coming in, that the inversion layer is staying stable, things like that. And also like paying attention to our satellite cams, making sure that there's no inclement weather coming in. I think that's going to be the last OG for the night, and then I'm going to move on to flats.
Okay,
I don't know
all
if you
right.
can hear the slewing from the telescope in this room.
Yeah,
I think that'd be really cool.
I'm not exactly sure. It's even if the sound feels loud for us,
Yeah.
it could be canceled by
Mhm.
Zoom. So one other thing that we take care of usually when we are assessing conditions is the particle counts.
Oh.
So Lisa, do you want to talk a little bit about the particle counts?
Sure, yeah. We unfortunately have a volcano that is going off on this island, and it is constantly spewing smoke of some kind, noxious gases. But when it is actually spewing lava, a lot of times it will throw a lot of dust, very, very fine dust up into the upper atmosphere. And those particles will, if the wind is in the right condition, it will either swing around the south side of the island and come back toward us, or if the wind is straight from the volcano toward us from the southeast, then we will get directly some of that particulate matter. And so we have sensors placed throughout our building where we can actually detect whether or not there are particles being blown around. And Normally for the day of and the day after it actually is spewing lava, that's when we have to be a little more vigilant of the particulate counts, because that's when we will start seeing some of that particulate matter. And when we do get the high counts, we have a threshold above which we cannot open. So we'll stay closed until those particulate numbers go down.
And right now, there have been a few wildfires on the Big Island, and there was a fire very recently on
On the slope of Mauna Kea, yeah.
on the slope of Mauna Kea.
Yeah.
So, what were the kind of conditions that were happening here? I mean, affecting the summit conditions due to such
Yeah.
a wildfire?
Yeah, absolutely. When we have wildfires going on, especially around the mountain, we will get some of that smoke up over the summit. And sometimes they'll be able to actually smell it. Sometimes they're also able to smell the sulfur from the volcano at the summit. But when they can smell smoke at the summit, we know the particulate count is also going to probably be a little high. And so we have to be aware of any fires that might be going on, especially around Mauna Kea.
All right. So I think at this point, if there are any questions, we would be happy to take any questions.
You guys have questions about, kind of the stuff that they've been talking about so far? Anything about CFHT or observing in Hawaii? Calibrations, MegaCam? Maybe I can ask a quick question.
Sure, yes.
So I'm curious about, oh, sorry, let me fix my video so you can actually see people. There we go. That's better. Sorry. So you mentioned the skiing, and so I was wondering, like, what types of skiing are like really good weather, and what types of skiing are bad weather, and what kinds of projects do you tend to do based on what the skiing is?
Yeah, that's a really, really good question. Really good seeing is usually 0.55 to 0.65 is what our astronomers can ask for. Sometimes they'll ask for less than 0.55. For those, they usually ask for ideal conditions. These are the programs that some of them are doing astrometry. So they need the stars to be really compact so they can do very good astrometry and positioning of the stars. They might be following stars that are moving. They might be doing parallaxes. So they're observing on one side of the sun and then on the other side of the sun, and they're doing a parallax to get the distance to that star. So for really good seeing, we need that. Also for very distant objects, we want really, really good seeing, especially if they're looking at galaxy clusters, for example. They might want really good seeing so they can actually categorize the galaxies in those images. For less stringent conditions, 0.8 to 1 is another range. We have 0.1 to 0.12 arc seconds, and then above 1.2 arc seconds. Above 1.2 arc seconds is usually our snapshot programs. These are people who are most likely doing photometry, and they just want the magnitude of the star. So as long as we get them data, they can use larger apertures to actually do the calculations and get the magnitudes of the stars. And kind of in between, they're doing pretty much everything. We're looking at follow-up on asteroids, near-Earth asteroids and asteroid belt objects. We're doing a lot of stellar astronomy as well. They're looking at various star clusters, for example, to see what stars are members of those clusters. They're also looking at, distant galaxies and distant clusters. So it can be a large range of things. But the nice thing about our keeping on top of the conditions is we can optimize the programs we do for the conditions that we have. It used to be that an astronomer was assigned 3 nights. They would come here, maybe the conditions weren't optimal for their program. And so now we get to actually optimize all of that and make sure that the images that we're taking are in the constraints that the principal investigator asked us for. So.
Thanks. Other questions?
I guess I have one is when you showed the collage of all those like images together, I think you mentioned it was like, was it one portion of the sky or was it like different regions of the sky? And how did them?
That image she showed is actually one area of the sky. So that's one pointing right there.
Yes, so this is basically the field of view of MegaCam. So when you point MegaCam on the sky, this is like one patch of the sky, but it's a very wide patch of the sky. It's 1 square degree by 1 square degree on sky. So it's pretty wide. And it's a mosaic of 40 CCDs. So there are 40 CCDs in there. And let me show you the scale for the CCDs. Just give me a second.
Yeah, and just so you know, not all of the CCDs are butted up against each other. So there may be tiny little gaps between them. So if we're doing a mapping, we might do a dither pattern that will fill in those gaps. And then they can add all those images together to get the entire field there.
So this is the actual CCD mosaic, and you can see. I think it's a dime on the bottom left, just for scale. Not exactly sure what that is.
€2.
So that's the CCD mosaic. It's 40 CCDs. When we take the images, as Lisa said, they're not attached to each other. These are like independent independent extensions, for example, for a FITS file. And we basically want to stitch the image together when we are generating the final image. And that goes as a part of the pre-processing that we do over here at CFHT. So, you know, the entire process of generating the final images, it includes cleaning up the image, flagging the bad pixels, correcting for bias, correcting for flat fielding. So that's why we also have flats, which Jessica will be starting, or she's almost started them.
I'm gonna start soon.
Okay,
So
she's
now,
gonna.
we're going through a focus sequence and then we'll
Okay.
go on to flats.
Okay, so she'll be starting flat soon. So doing the flat fielding, and then stitching the images together, and then calibrating them. So it's a part of the whole process. But yes, you need to stitch the the different CCD images together in order to get the final image. So at this stage, I'll back up a little bit, and I'll cover at least a couple of examples of the kind of science that we do over here at CFHT. So this is one image. This is of a group of galaxies called the Stephan's Quintet, popularly known as Stephan's Quintet. The Stephan's Quintet is somewhere over here. If you can see my arrow on the screen. But this is the broader patch of the sky, which has the Stephan's Quintet. The reason we were capturing this image is we wanted to study all the diffused gas in the entire patch, in this patch of the sky. And so this is called a low surface brightness image, where we try to get the diffused features prominently in the image. So this is a very specific mode. And Lisa, is there anything specific that you take care of when you are taking images, for example, in a low surface brightness mode versus a regular MegaCam image?
Yeah, absolutely. What we do when we are taking these images is we want to, number one, make sure that the sky is not varying terribly much. So we want to make sure that the sky background is pretty much uniform as we go through and take these images. We usually take the minimum of 7 images in order for them to do this flat fielding that they do with this. What they do is they median filter out everything that's in the images and create their own sky flats so that they can reduce that use that to get rid of the pixel to pixel variations within the images. And that will bring out a lot of these very, very faint wisps and gaseous strings here and there. So we do have to be very, very careful when we're doing this and making sure that the sky remains pretty stable. And we want to get a minimum of 7 images. We also want to make sure that we don't do the same image twice in a row, because they want to be able to median filter those images together, because they're dithering slightly as they go around here. And as they dither, they can median filter out all of the stars and the galaxies and everything to get that perfect sky flat that they need to actually get rid of that pixel variation. So.
Okay, so that's one example. The other kind of science, which we do a lot with MegaCam, is moving objects. So this is a GIF of 2024 YR4 moving in that red circle across the sky. So this is these are different sets of images, which if you see, you can actually see the moving frame. The object is moving in the frame, and that is 2024 YR4. So Lisa, again, a little bit about when you are observing moving targets, what is it that you specifically take care of when you're doing the observations?
Yeah, absolutely. As you can see in this image, all of the stars are trailed. That means that we are doing non-sidereal guiding, which means that we know, or we are given roughly an idea of how fast this target is going to be moving. And the telescope then is moving at that same rate, so that the image of the asteroid itself is stationary, but all the stars are going to be trailed then. So we're moving at the speed of that object. And we usually check and make sure that those values aren't really high. If the values are really, really high, sometimes it's hard for the guiding to set up. And in those cases, sometimes we go without guiding and we just let the telescope automatically do the non-sidereal without the guiding. And in those cases, the stars again will be trailed, but hopefully the asteroid itself is not kind of moving or wobbling a little bit in the image. And we can get a good image of that very, very faint target. And you can see how faint this target is as well. We like to do these in as best conditions as we can. And we like there to be no clouds. And occasionally we do get clouds. And in that case, we try to take many images in a row in order to try and get enough signal for these very, very faint targets.
Yeah, and there are there are specific requirements about what, again, sky conditions, what weather conditions are optimal for observing these targets. Not all of them need excellent conditions. They are pretty doable in average conditions. It's just a question of reaching the right signal to noise when you're taking these images, so that you're able to point out your target. And if these are bright targets, then it's pretty easy and convenient to have these observations even during just close to the twilight times as well. So that's another that's another type of programs that we do more for the University of Hawaii astronomy group with CFHT. So
Can I ask a quick question?
yeah, sure.
So could you say something about, the other artifacts that are in the image, and where they come from, and how you distinguish between those and the moving target?
Yeah, that's another problem that we have, is that our CCDs are really, really good at catching what we call cosmic rays. And so a lot of those little dots that you see kind of moving around, some of them might be elongated. Those are cosmic rays that are going through our detector. And unfortunately, those are white noise to us. And when we see a target that we know is moving, we can tell that that's the correct target, as opposed to all of the cosmic rays, which are just kind of random throughout the sky. So a lot of times you're kind of looking for something this faint with all of these cosmic rays around. But a lot of the astronomers have an idea of where they're going to find their target. And so they can look in the right area to actually see this. And they also use some of them use software that will actually find the target for them too. So
Thank you. Any other questions? Oh, we've got another question in here.
Sure.
Is that black strip like on the right side, is that from the stitching or is that like just a CCD artifact too?
you mean the black line?
Yeah, yeah.
Yeah, that is an artifact that sometimes comes in. Remember, we do 3 images and sometimes we slightly move it, but in this particular case, those are probably areas where we just had something really, really bright that we just had to filter out. And so that is just an artifact of the processing of the images.
Cool.
Any other questions? Oh, yeah, we got another question.
Yeah, why do we sometimes see purely white images? Like there's nothing in the images, but we do have the received images from the telescope.
Were you able to hear that?
Not quite. I don't understand the question.
So have you gotten data from
Yes, so
CFHT?
if we have the archive data, there sometimes has a list of white images which has nothing in there, but we still receive them. So what could cause those images to exist?
I see what you mean. If you're getting images that have nothing in them, they could be calibration frames. So we take a number of different calibration frames. Some of them look like they're just noise. Those are usually the darks or the biases. And the reason we take those is because there is a signal that we get from the amps as we read out the images, and that has to be taken care of. So that's kind of white noise within the electronics itself. And then the flats, normally the flats will also be blank, and those are used to get rid of the pixel to pixel variations within the image, because each pixel has a different sensitivity. And so as you're taking images, you have to flatten those out and get rid of that sensitivity, the varying sensitivity of each pixel in the image. So,
I'm actually taking flats right
Yeah.
now.
so.
Mhm.
So really, we're taking images right now. The sky is getting pretty bright. The sun is another 15 minutes away from rising, but we're doing in this bright sky right now, we're taking flats in some of the filters that we use tonight. We try to get a certain number of flats so that we can median filter them together. And if there are stars, sometimes as we start these, we will see stars, but as the sky gets brighter, those stars will disappear and we'll just get a blank field. And eventually we take all of these flats through this entire run and then combine them all to make a super flat that we use to and then flatten out all of the images taken during the run. And what that does also is if there are any pieces of dust or something somewhere in the optics, you'll get these donuts. Those will get flattened out as well. So.
This is just like CFHT.
So, yeah, so this is an example of a flat image, and as you can see right now, we are seeing stars in there.
Yeah. And as the sky gets brighter, those stars will disappear just because the sky background will overwhelm the brightness of the stars. So.
And the flats are taken in all the filters. Ideally, should be taken in all the filters that are currently on the wheel.
Mhm.
So for every instrument, there's a set of filters that is always mounted with the telescope. There are active filters, and then some of the filters are taken off as required for the programs during a specific run. So for MegaCam, for example, I believe there are 8 filters that
Mhm.
can be on the instrument at a time. U, G, R, I, Z are our most popular ones.
And GRI.
And GRI, yes. Yeah, GRI is very popularly used for
The
moving
asteroids.
target.
Yeah.
Yes.
The asteroids, yes.
Yes, so UGRIZ and GRI are popular filters. So when flats are taken or when standards are taken, these are the calibrations which need to be done in all the filters, so that whenever we can use the data for a specific night or during the run, we are able to get master flats prepared for all of the filters that we have done science programs with. So that is one other thing that the ROs have to take care of when they are doing the standards or the flats, that they have to make sure that they observe at least all of those filters for which we do the science programs during the run. And it's a matter of time that they have to manage it well. Sometimes there could be competition between completing a specific science program and getting sufficient standards for a specific run, and that is something that the ROs have to address or coordinate with the Q coordinator. So these are astronomers over here who are responsible to make cues for a given night to decide what should be the right priority and what we should go forward with. But yeah, so that's what we're doing. So this is an example of flat. I'll show another example after some time when we do not have some stars. But now that we are talking about cues, I would like to talk a little bit about how we actually schedule observations at CFHT. So over here, we do remote observing. As I mentioned earlier, we are in the control room in Waimea. We don't have to be up at the summit to do our observing. So what we follow is a queued service observing mode. And what that means is for every night, we queue our observations for whatever science that we need to do. So over here, we have resident astronomers. I am one of the resident astronomers, and one of our duties is to actually schedule observations for a night. So CFHT, how it operates is it usually has one instrument at a time. So right now we have MegaCam, and the instrument runs could be anywhere from like 4 to 5 days to all the way to 10 to 14 days. Right now, MegaCam has a 14-day run. MegaCam and one other instrument, Spiru, usually both of these instruments have long runs. So we have one instrument at a time, and we have different astronomers who are responsible for different nights in order to do these scheduling part of the observations. So based on all the science programs that have been accepted on MegaCam, and based on which targets are visible during a specific time of the run, and depending also on the science priorities, so whether it is an A rank program or a B rank program, or a C rank program, or whether it is a snapshot program. And by snapshot, I mean snapshot programs accept any sky conditions for their observations. So depending upon what is the rank of the program, and depending upon which targets are visible, astronomers schedule the observations, and these are typically grouped in different observing groups. So there could be one single instrument configuration for a given observing group, which has a lot of exposures in it, or these could be different configurations, but if the targets or the fields need to be observed one after the other, consequently, then they are grouped together in a given observing group. And then we have different observing groups lined up all throughout the night. One thing that we have to take care of while scheduling these observations is not every time we will have ideal sky conditions, right? There can be different weather conditions depending, there could be different seeing, there could be variable clouds, and there could be high humidity. So depending upon different conditions, we need to plan accordingly. So we typically tend to make cues based on weather conditions. So our first cue, or our main cue, is usually the one that is for excellent conditions. When we have excellent seeing, there is no humidity or absolutely no clouds. But then we also plan additional cues if the seeing is for MegaCam, usually when we have average seeing, and then one cue when we have very poor seeing conditions. And usually the snapshot programs are the ones that go in the very bad conditions queue. So that's one other thing that we take care of when we are scheduling these observations. Just to, again, talk on a broader scale. So MegaCam is our one instrument, but we have another imager in the near infrared. It's called VirCam, the wide infrared camera. And the kind of science that Lisa was talking about, we do a lot of astrometry. We do a lot of astrometry programs with VirCam, for example. So VirCam generally needs really good sky conditions, especially in the seeing part. Our instruments are also kind of have distributed dark and bright time. MegaCam, for example, uses all the dark time. Well, CITEL is also another instrument that uses dark time. So MegaCam and CITEL is our spectropolarimeter. No, it's not a spectropolarimeter. It's a
spectrograph.
interferometer. So it actually does spectra and images both. So CITEL and MegaCam need dark sky conditions, whereas for our other three instruments, VirCam, Spiru, and I'm forgetting the last one.
And Espedance.
So for those three instruments, we need bright conditions. So Spiru is our near infrared spectropolarimeter, and Espedance is the sister instrument, which is also a spectropolarimeter, but in the optical. So those can be done with bright conditions.
You guys know
But
what dark
that's
bright conditions are? Can you tell us what dark and bright conditions are?
sure.
Yeah.
So dark conditions are when for example, the sky background is dark. So for that, we need to ensure that it's not close to the twilights. We need to ensure that the moon is not close to the target and not as much illuminated. So there is, so we actually, when we are scheduling observations, for example, we have a lot of information about how the sky is, when there will be sunrise, when there will be moonrise, when there will be sunset, how much is the moon illumination. You know, if it is 10%, it's sometimes okay, like 10%, and the target is, say, for example, 45-50 degree away from the moon, then it may still be okay for some programs. Some programs may need it 90 degree away from the moon and at 10% illumination. So they need more darker conditions than some other programs. So depending upon those conditions, we can define how much dark is the sky. Generally, we define it, there are three levels. There can be dark sky, there can be gray sky, which accepts some kind of illumination or some or some closeness to twilight should be okay in those conditions. And then there are bright conditions when the moon is up in the sky, but it really doesn't matter for the purposes of the program. And this can be the case when you're observing bright targets, right? Maybe the moon is not such a big problem for your targets because your target is going to be very bright. Do you want to add something to that, Lisa?
Not really. I think that covers everything pretty much.
Any other questions?
Yeah.
Yeah, how is seeing determined by the program? Is it a kind of averaging step based on the star observed?
So
Did you?
so was the question, how is seeing determined for a program?
Well,
Yeah.
the question is, how are you measuring the seeing? Like, is there a program you use to determine what the seeing is?
Okay, so I'll let Lisa
Yeah,
answer that.
we actually have two different ways of checking things, but we have a camera on a tower outside the building, and that will kind of give us a general idea of what the sky conditions are like for the seeing. But we also have a quick look program that actually will quickly do a calculation for us. Actually, we have two of them. We have one on our viewer, so we can actually go into our viewer, and our viewer will do an automatic calculation just from one of the readout sections of this large array. And usually we use one of the four in the middle of the image. As you get to the edge, the seeing might not be quite as good, but we use the center to do that. And then we also have a what we call elixir. This is an elixir. We have a program that actually does a quick look and puts it into the header for each image. So each image that is read out has a header that has all the information about where we were pointed, what time it started, what time it ended. All of that information is saved. And it also saves a quick look IQ estimate. So we can actually use our image viewer, calculate what the seeing is there, and compare it to the quick look one that we get in the image header. And when those kind of agree or they're pretty close, we know we're doing pretty good. So that's how we actually check it as the images are coming off the telescope, just to make sure it's within the range that the PI requested. So
on the plot you're showing here, the top panel, is that the measured seeing in arc seconds then? And then it's
yes.
over time, so you can kind of see that you had a really nice period for a while, and then it just went all wonky.
Yeah.
Yes. So that's arc seconds, and that shows us, that's from our dim and on the weather tower, and that actually does show how variable the sky can be when we get some turbulent layers above us. And there is a turbulent layer still above us. Even though the clouds are down below the summit, we still do have some turbulence occasionally in the upper atmosphere that will cause seeing blow up. So
Thanks. Did that answer your question?
Most of them for programs.
Actually,
So like,
right.
I want to ask about like more about the algorithm. Like if we have an image with thousands of stars, did the program just estimate the thing based on averaging the fitting results based on the hundreds of stars?
So I suspect, so we're asking about if you have like thousands of stars in an image, you know, if you are looking at an average value for what the seeing is across.
What we do, this is like we said, this is a 1 degree by 1 degree field. That's why we use the center portion usually. So we pick so each of the CCDs in this array has 2 amps that read out. Now we do that because the readout can take a very long time to get each image off. And so right now we've got it down to about 45, 46 seconds, which is really good, but it takes that long to read out the images once we take one. And so we usually when we're doing our quick looks, we're using one of those readouts that's in the middle of the image, because that is where the best seeing is usually going to be. And that's what we go by usually when we're actually measuring that. So. Any other questions? Did that answered your question, right? Okay.
I have a general question. Just what kind of background do you have to do these observations? Just explain how you get to do this.
Yeah. If you're asking, I'll let Viraja go first. She's the PhD.
Okay, so I would just cover for myself. So for an astronomer, you have to be a PhD. So astronomers are typically, so as an astronomer, my duties are generally distributed between number one, all the support duties for nighttime observing, and that includes scheduling observations for every night. And it also includes doing technical reviews for incoming proposals. These could be either for large programs, or this could be for the regular PI programs that we have for every cycle. Other set of my duties is to do any programming work or instrument managing thing. So as a resident astronomer, I'm also managing the WIRCam instrument at CFHT. So this is again our near infrared camera. So as part of managing the instrument, I basically have to take care of the technical reviews for that specific instrument. I have to plan for for a given semester. So at CFHT, semesters are divided into there are 2 semesters, each of 6 months. So right now we are in our 2025 B semester, which started 1st of August. And so for every semester, I have to take care of planning for different runs during the semester, and that depends upon what all are the accepted programs, when are the targets visible, and all those things I have to take into account when I'm trying to plan out how the semester will look like in terms of observing with WIRCam. I also have to take care of the reduction and pre-processing of the data at CFHT. So once a run is complete, so we just ended our WIRCam run this past Thursday. So after a run has ended, I have to take care of doing the calibrations, like making master flats, master bias frames. I have to take care of the initial part of pre-processing, which is basically reducing the data. And we provide reduced data to all the PIs. So we distribute that. So I have to also take care of the data distribution. So just making sure that all the data reaches the astronomers how they have asked for it. So that's complete cycle of things. The observing part, however, in between is what the remote observers do. There is third part of my job is time for my own research. So I actually work on supermassive black holes and AGN. I study gas motions around supermassive black holes, mostly in Seyfert-1 quasars. So so I have some time for my own research where I get to either work with instruments here at CFHT or anything else that I want to do for my research. So that's everything that's in my job, and I'll let Lisa cover what she needs as a remote observer.
Yeah, you were, I think, asking a little bit about background. I actually got my undergraduate degree in math, computer science, and physics at a small liberal arts college, actually. And from there, I went on to grad school in the physics department, physics and astronomy department at the University of New Mexico. I never did finish my degree there. Unfortunately, a lot of the men there were the old boys society, and they looked down on women, and I was not treated very well there. So I ended up applying for a job down in Chile, and I went down to Chile, got the job down there, and worked there for 5 years. I was one of the data reduction specialists. So essentially, I was teaching people how to reduce their data with the IRAF package that was used with the National Observatory. So I was the IRAF expert there. And I also was collaborating with a lot of the astronomers on staff there, doing a lot of supernova research. When I got down there, supernova 87A was still naked eye visible. And so I actually got to see it naked eye and watched it fade away to nothing. And I worked on that supernova as well as many other type 1As and type 2 supernovae with the team there, and put together did a lot of the observations as well up at the summit. So I've used pretty much all the telescopes at Tololo, and had a great time there, published quite a few papers. So I have a couple of first author papers and quite a few other big collaborations that I'm a part of. I was not, however, a part of the High Z team. I'm kind of pissed that I was not asked to work on that. But the High Z team that won the Nobel Prize, I know I collaborated with all those guys. So I've actually collaborated with a lot of these Nobel laureates. And from there, I actually went back to Tucson, and I worked at Kitt Peak for 2 years, also doing similar stuff, managing the tape archives, doing a lot of that sort of stuff, as well as teaching people IRAF. And I was at the summit 2 nights a week to help people to make sure they had everything they needed and knew what they were doing when they were observing. I've also observed at almost all the telescopes up on Kitt Peak as well, because I was working with many different other people collaborating, or I would be with people who had time, who got time there, and they would say, hey, come observe with me, and I would go observe with them. So you get to know a lot of people. This is a pretty small field. From there, I actually went to I started taking classes at the University of Arizona on the side because they paid for it as I was working at Kitt Peak. And one of the professors there happened to mention, why aren't you a full-time grad student? And I said, would you take me if I apply? They said, of course, we know you. You're doing well in your classes. So I actually then became, after 2 years at Kitt Peak, became a full-time grad student, got my master's degree in astronomy. And in that time, a friend of mine went down to Chile. I had come from Chile. And then he came here to CFHT. And when I was starting to apply for jobs after I got my master's, this was one of the places I applied for. And I didn't know that this person was working here, but I knew him, he knew me. And I blame him for getting me the job here, but I've been here ever since. So I have a master's degree. Some of our ROs just have undergraduate degrees in astronomy and physics. So it doesn't take a lot to necessarily to to be working here, but you get trained on all of this, how to observe, what you're doing, all of that. We give people time to get to know our instruments, get to know how to observe with each of them and what they need to look for each night. And so my main job, are probably 65 to 75% of our job is sitting right here doing the observations. And so once you get trained in all of this, it's fairly straightforward. You get into a routine of being able to do things. From there, you all do side things. So I do a lot of outreach stuff like this. I do some of our website work as well. And then I also do some other menial things. I used to work in the library, but we kind of phased out our library. So, and then I was also working for the MSE project, which was also kind of phased out just now, mainly because the money hasn't been coming in for that. But I've been doing a lot of other things with people on staff as well. And so the rest of our time is put in doing other things, other duties for the observatory. And you know, we can pretty much pick and choose what we want to do. And if you want to do science and you can find an astronomer that will work with you, great, you can do science too. So it's pretty nice. And you can get involved with any of the engineers to work on any project that maybe needs work up at the summit as well. So, and I will pass it off to Jessica.
I'd like to share my background and also give a quick update. So I just finished the night. I just finished flats. We're shutting down the telescope, and I think we have some cool stuff to share as we do our shutdown procedure. And I'd like to share my background because I feel like I can relate to y'all. I graduated like last year, actually. I haven't been here a full year yet, and it's pretty surreal, but I'll give my background. I'm also all over the place because I just finished this 13-hour shift.
Yeah.
But yeah, okay, my background. I'm here from Hawaii. I was born on Oahu and I went to McKinley High School. And then I went to the University of Rochester in upstate New York for my undergrad. I did physics and astronomy as my bachelor's. Upstate New York in Rochester. I actually visited Toronto more than I visited New York City during those 4 years. Toronto's great, by the way. You guys have amazing Asian food because I won't talk about Rochester's Asian food. That's going to get a little off topic, but yeah, I did physics and astronomy. I did 2 REUs, which is, I'm not sure if that's, I'm going to talk about REUs. I did 2 internships. I did one in physics and astronomy, one in physics education research. At the University of Rochester, we have our own observatory called MEES. I did some projects doing that, and then I ended up coming back to Hawaii because I realized, why am I doing astronomy in upstate New York when it's so cloudy all the time? So I came back home and I've been here for almost a year now, and it's been really awesome.
Yeah, REUs is basically research internship programs, very specific ones that are for undergraduate students in the United States. I myself was a part of the SERP program, so I was in where you are right now many years back. So it's really very fulfilling to see that I'm able to bring this back to you guys. So hopefully this was very good. And I think I'll pass it over again to Jessica to give us an update of what's going to happen now.
Okay, so now we're gonna go through our shutdown procedure. It's been a long night. We need to make sure all the hydraulics, all of the machines are still working and functioning properly. There are things I need to do. I need to go through all the observations and make sure I have all my comments filled out, all my weather reports filled out. I need to write my end of the night report on top of all these reports, kind of summarizing everything together. Anything else I should mention specific for the shutdown procedure?
Not really.
Yeah.
Oh, and the dome is closing right now, actually.
So this is our prime. So what you see in the image on the left hand side, this is the primary mirror. The mirror covers are now closed. And now I believe it will be the shutter.
It's
Yes.
moving already.
I can
Go to that.
And this is the shutter. So it's now closing.
Very slowly.
It moves very slow. So
It
you
takes
can
about
see-
8 minutes for the shutter to open and close for the opening the dome. Yay. And I would turn up the noise so you can listen
Yep.
because you don't want it to break and not hear what's going on.
Oh.
Yeah. So we like to listen to this when it's opening and closing. We also like to listen to most of the things as they're opening and closing, mainly because we have had occasions in the past where one of our motors broke or one of the shafts broke and pieces fell from there to the floor of the building. And in that case, we have to stop it from closing and make sure that the day crew or somebody goes up to check out what's going on with it, because we can actually run on just 6 of the 8 motors. We have 8 motors that drive this open and close, but we can actually run on just 6 if we have to. But if anything does happen or we hear something, especially even during the night, we have had boxes that are mounted on the back end of the telescope fall out when we've moved to the wrong direction and it wasn't properly bolted in. And so when you hear crashes in the dome, you want to stop and turn on the lights up there to take a look and see what happened. So.
Yeah, it's quite amazing. You even have locking pins for the telescope. And when the locking pins go, but maybe it does not make quite a big sound when it goes out, but
Yeah.
when they go in, it makes a click sound, and you want to listen to that click sound in the control room so that you know that it has happened, the action has taken place.
Yeah. So essentially we have, back when we used to do classical observing, astronomers would get assigned a couple nights at the telescope and they would fly here from France. They would go up to HP, they would stay up there at the 9,000 foot level in the dorms. And then we would drive them up to the summit at the start of the night. We would make sure everything was ready to go and get ready and set up for them. And then they would tell us what targets was next in the program. So we were more or less telescope operators for them and they operated the instrument. And when we decided that we wanted to go remote and work from downtown, there were a lot of systems that we had to push buttons for or be up there in order to move things. And, turning on and off lights, you don't think, okay, if we're going to be remote, we need to be able to see stuff. We're going to have to automate all the lights The dome shutter was one of them, opening and closing the mirror covers, raising and lowering the windscreen, and various things like that were all automated for this project so that we could come down here and have more brain cells, hopefully, to do the observing for the astronomers. So now, instead of getting assigned a couple nights and they come here and they get completely weathered out and go home with no data, we are here downtown. They get assigned maybe 10 hours to do their program. They ask for a specific amount of time. And then we try to go through and get as much of their program done as we can. And usually you can give them the completeness of the programs, but obviously we try to focus on the A programs, and they usually get the most amount of coverage, and they are the best covered of the programs. And then it kind of goes down from there, but you can.
Yeah, so generally for programs, we target the A programs, so we try to complete them as much as possible. For WIRCAM, for example, all of our A programs are almost 100% done. For MegaCam, it can vary because MegaCam has a lot of programs. It is very much in high demand. But we try to finish most of the A rank programs. The B and the C are the next, so they don't get as much completed, but it's still a good completeness level, at least 60% or more. For our large programs, we aim to do them 90 to 95% complete. For our previous semester, I think our previous set of large programs ended in the previous semester, 2025A. And we completed both our large programs. One was of CFHT, which is one of the programs where Canada is a partner in. So there was CFHT, and then there was another one which is I'm forgetting it.
Yeah, I know.
Oh yes,
Yes.
it is for the for observing the planet, the search for planet 9 science. It's a classy program which Wes Fraser at NRC he leads it. So there were two large programs, and we were able to complete both of our large programs. The previous set of large programs. Our next set of large programs has already started in 2025B. That again covers CFHT, and it also has another one which is a pristine program. And then there is another one, I believe, and I can't remember what that is. So I'm really sorry about that.
And
but yes, we have large programs.
Yeah, and there are a few programs that are actually doing follow-ups of those large programs because they found something really cool and they want to investigate it even more. And so that happens a lot too, where we have a lot of data that's taken on a specific field, and then they like, okay, we want more of this.
So right now the shutter is closed. These are the views inside the dome. So you can very clearly see that the lights are on. That's because Jessica is checking where things are, if everything is in place. Nothing is unusual. There are no leaks. There are no spills or anything. So lights are still on. Once everything is done and Jessica finishes all of her checks and everything, she's going to turn off the lights. And that will be the end of the night for her, at which point she will be sending out a night report. And I believe she spoke a little bit about the night report, but night report is basically where the RO summarizes everything that happens during the night, starting from how was the weather, what were the fluctuations in the seeing, if there were any fluctuations in the fog, in the humidity, what are the specific observations that they took. So all of the OGs with specific programs that were observed. So all of the observing groups. They also list if there were any problems. For example, if there was a technical issue, say, for example, they sent a command to the dome and something did not work properly, or something got stuck and then it again started working. So that if there are any glitches, they are very particular of explaining all of these things in the night report. That's because the night report is the go-to a summary of every night for everyone over here. May it be the astronomers, may it be our software people, may it be our engineers, our operations people, the ROs, all of us take a look at the night report for every single night, and decide the next course of action for us in terms of planning for every night. So is there anything else you want to add to that, Lisa?
Yeah, there are, we also do a time accounting in our log for the night as well. So any time that is lost there, we will mention and give more details so that the people who are checking things out during the day have some idea of what exactly happened, you know, what was the sequence of events. And we have to be very detailed and make sure they have a timestamp on that so they can go back to the logs, find that time range and see what happened and try to figure out what exactly happened. So timestamps are absolutely imperative a lot of the time for when we have problems. You know, that's kind of generally the main part of our job is really just once we're done observing, just make sure that we give all the information from the night that they need. So
what you're seeing in the image there, is a part of the it's the top part of the telescope where we usually have the secondary mounted. But right now there is no secondary over there. There is no secondary mirror. What you see over there is this instrument, and that is MegaCam. So our two imagers, MegaCam and VirCam, are at prime focus. So when we want to have MegaCam or VirCam, we basically remove off the secondary, stow it away very carefully, and we mount our instrument on the top over there. So it's a long instrument, so you can see it's getting pretty close to to the shutter.
yeah,
But
it looks
safe.
a lot closer than it
Yeah,
really
yeah.
is, honestly.
Yes.
So,
But yes, any other questions?
I have another one. Just how easy it is to work in a different observatory from, let's say, working in the Hawaii one. If you were to want to go to Chile, let's say, how easy it is to transfer between the two.
that's a good question, actually. I actually grew up learning French. So going to a Spanish-speaking country, it was very easy for me to pick up the language fairly quickly because it's a Latin language and a lot of the words are similar but pronounced slightly differently. So I did learn a lot of Spanish living down in Chile. But we had what we call the recinto in Chile, and there are about 40 houses where a lot of the foreign hires lived. So we actually all lived together. Like it was like a mini air base or a mini army base, right? They had all these houses and we would live in those houses. So we actually had parties with each other there. Most of us were English speaking, and a lot of the day-to-day stuff was all in English. Occasionally we would get Argentinian astronomers to come observe, sometimes, you know, people from other countries. And, you know, we pretty much spoke in English most of the time, but it was a wonderful experience being down there. And if you wanted to go to lunch, a bunch of us would pile in a car and go downtown and go have lunch together, or we would actually walk downtown. It was a bit of a walk to get downtown, but it was nice. And you know, the open air markets, you know, you don't get a lot of farmers markets everywhere. We have them here in Hawaii as well, but the farmers markets in Chile, in La Serena, were phenomenal. And it was really good. You got a lot of good fresh food. Living down there was wonderful. Being here in Hawaii, I would say is a little more isolating in the sense that this is a pretty, you know, even though it's a big island, it's pretty small. That's not a huge population here. If you lived over on Oahu, you probably would have more exposure to a lot more people because that's where the main population is. But you know, it's pretty much kind of like living in the country here in Waimea because we are surrounded by ranches. So it's mostly ranching country. And it's pretty quiet. The streets kind of roll up at 9 o'clock every night. So, you know, you're not out partying very late in the evening unless you're down in Kona or over in Hilo where things are open a little bit longer. But yeah, living here is, I would say, just like you would be living in the country, probably somewhere in Illinois or Iowa. I'm originally from Illinois, so but I grew up in the Quad Cities, and good area, a lot of people there, but it's not a far drive to get out into the country, and it's pretty nice. So living in Waimea can be a little isolating, but we do a lot of if you need something, a lot of times you order it online and have it mailed. So
I've not. I've visited Chile for a summer school at Aura. So
Oh, yeah.
I've been to the Gemini South Observatory there. And while I was there for approximately 10 days, I was not able to grasp a lot of the cultural aspect, although I did a little bit of Spanish just for the greetings and for the food. But being here in Hawaii, I would say the difference also is about understanding the culture and delving with the culture when you want to work at some location like Hawaii. Hawaii is very strongly influenced by both Japanese and American culture. So trying to understand a little bit about how Hawaii is, delving with the people, actually going out in the community, is all a part of how you will thrive at an observatory as well, because you have locals even at the observatory, not that many, but there are still people who are Hawaiian, and understanding the community a little bit also helps for you to thrive in the organization itself. So that is also one thing that for me as an astronomer, I am originally from India, but I am a Canadian. I've been in Canada for more than 14 years. And moving from the Toronto area to Hawaii was definitely not a trivial thing, because Hawaii is so much, as Lisa said, it's very isolated, especially Waimea, because it's such a small town, almost like a village. So trying to understand the culture, the place where you will be situated, where you are working, is another part of getting to know the community and working at an observatory.
yeah, and Chile, I would say, is very European in the sense that they take their long siestas at lunch. A lot of the restaurants downtown won't open for dinner until 8 or 8:30 in the evening. So you know, they're open till midnight and 1 o'clock in the morning, and that's when people go out to eat after their siestas in the afternoon. So yeah, very, very kind of European culture almost down in Chile, and Spanish, a lot of Spanish influence, but yeah. So it was a great experience though, being down there. Any other questions?
I think that's all good for us.
Okay, so thank you, everyone. It was a pleasure having you all. Thank you for all the questions. And we really look forward to doing more sessions for this program in the future. But thank you
Awesome,
so
thanks.
much. And thank you, Jamika, for hosting and supervising all of the session. Thank you.